So let's start with the contents of the talk. So first, as I mentioned quickly, so I'll introduce some application and driver behind AI. Discuss a little bit on the AI fairy tale, as in what do we think and what actually is the reality, and also then discuss a little bit on the production challenges, give you a 101 on that, and then eventually touch operationally how such production challenges can be tackled through what are the approaches which we can take to address those. And then I will end up with two use cases specifically from the telecommunications industry and the automotive industry. And hopefully some of those experiences you will find useful. So with that, here are some, let's say, flagship applications from ML systems or AI. Sometimes I'm interchangeably using them, the two terms ML and AI. The reason being that here I'm talking about the whole systems as opposed to an algorithm. And as I said, the flagship applications are voice recognition as an example, image recognition, and so on. And the key point or the take-home point here is most of these systems have achieved human parity or have actually beaten the humans on those tasks. That means the systems are really, really powerful. Also on the academic side, if you see, there's a lot of research happening in this area of AI. And on the bottom left, you can see we are generating about 100, on average, about 100 articles or publications per day in different fields of AI, computer vision, and robotics, and so on. And likewise, on the industrial side, you can see there is a lot of movement on the merger and acquisitions of different companies, startups, and so on. So that scene is also really, really active. And this is all the motivation. This all sort of clarifies that this is not just a hype, so to say, where people are putting money and so on, but really a lot of work is going behind. And that's why we need to really talk about end-to-end systems as opposed to a singular algorithm development. Very quickly, two key drivers why AI systems have picked up this kind of activity, as I showed on the previous slide, are the amount of data which is available today through IoT devices and so on, and connected systems overall. And the second thing is, of course, the processing power. And these two things combined have actually led to this sort of a surge in AI applications. But of course, we need to be wary of the pitfalls as well, which could have not only, let's say, performance implications, but really moral and ethical implications as well, which is a big topic these days in context of these systems. I have listed two here. All of us probably remember the Cambridge Analytica file story. Then, of course, there are misuse of applications, for example, mapping applications where drivers alert each other of presence of a police car, for example, which could be used by a criminal to game the system. And these are the things which we really need to take care of when we're talking about this end-to-end system design. And here is this AI fairy tale, as I mentioned on the content slide. So if you look at the top, so we have data, we do some magic, we get some value. People go one step deeper into that, and that's on the left-hand side, bottom left. So you identify a business problem, you gather data, you build a machine learning model, you tune the model, and you present the results. And if you follow these steps, you're gold. Basically, you get to numbers like what you see on the bottom right-hand side. I don't know, 84% improvements in the education sector, and so on. So huge improvements are promised based on these sort of strategy. But of course, the reality is different. And if you really do an analysis of what's going on the industrial side, barring a few players, here are the numbers, and these numbers tell completely different stories. So starting from the left side, so these are the companies obtaining measurable value from data, and this is just really 12%. And the companies who have actually deployed the AI systems to production, I mean, they come out to be about 15%. And that's where it sort of shows you that at some point in this cycle, there is a gap. And we need to really look into that. Otherwise, we have a huge business value challenge. And eventually, from a business perspective, if you have shiny prototypes and so on, you can show something great, but unless there is a value, and in this case, it's clear that this value is not coming through to production, so to say, this will fall off, and we need to cater that. This is just showing that visually. So on the left-hand side, we see the launch, and on the right-hand side, we see that operating is a hard part. And launching is not to claim that launching is easy, so to say. As I mentioned it here, it's just to give you a comparative analysis that we have done that. Last several years we have been there. Now we need to really talk about operation of these systems. What is this talk not about? This talk is not going to give you a strategic blueprint, so to say, of how AI systems are good and not. Not going to talk about the lack of talent problems. Not going to look at that we have a lot of silos. We are beyond that. What we are going to look at. So this what I said is basically depicted on the right hand side: workflow, business to models to presentation, as we discussed also a couple of slides back. Rather, we are going to talk about, starting from the bottom right, insight generation, the model lifecycle, and the production pipeline, and how does that play together with, let's say, the conventional development areas. So let's start with the production challenges. So what are these challenges? What are we talking about here? So there are probably gazillions of things. I mentioned umbrella items in this area. Compliance and legal is a big topic. For example, not only about your data privacy and so on, but overall systems. Is it really a validated system? How do you make sure that the old and the new does not clash? Reproducibility is a big topic. Can you actually make sure that whatever you're doing can be done again? Allocation of resources, a lot of times that's really a scarce commodity. So compute or store, for example, in your system or through cloud, if that's permissible, is that something which aligns with your AI production systems? Which vendors are you going to choose? Are you going to lock into those vendors? Do you want to keep open source? How much open source and so on? Edge to cloud. Do you want to have complete local solutions or complete cloud or a hybrid? Also a very big topic. What is going to be the latency of this system? So a lot of times you will have a perfect algorithm, a perfect system, so to say, but just that you don't have enough bandwidth in your production systems to allow for those communications which are happening: data download, upload, model insight, export, and so on. And of course, finally, the interfaces which we are talking about. Are you going to build new interfaces to these AI systems? Are you going to extend your current pack? To which extent? Are these the best interfaces and not? And these are some of the challenges, admittedly the major ones, which you come across, and then you have to dig into details of these. That how do we cater that? Pitfalls. When you have deployed a machine learning model into these systems, the model goes stale. How do you cater that? The model is not useful anymore. It has diverged. There are performance shifts in the system. How do you cater that? At which frequency are you going to update the system? So for example, is it going to be daily? Is it going to be hourly? Is it going to be weekly? What is the update frequency of these systems? When you have a self-learning or transfer learning deployed, is this something which you want to leave uncontrolled? What level of human interventions are allowed and so on? And then there are some best practices to address some of these. Look for a unified architecture. Look for an overall box which can make sure that things are orchestrated in a proper way. Don't build individual software components and put them together. Make sure you're monitoring important KPIs. That's really important. Also, more often than not, looking at the data is better than looking at the algorithm output. So look at your data already to see what's happening. Think about explainability of your models. Simple models are usually easier to explain than the complicated ones. Always have rule-based contingencies, so you're not always dependent on AI systems, so to say, from a machine learning perspective, but also certain traditional systems. In the end, if you do that, eventually you come up to, of course, real value. I'm not going to read the whole slide, but some values which are, I think, industry agnostic are: you have better uptime of your resources, you can save on capex and opex, time to market can be increased, higher revenue, and most importantly, which I think is really, really critical, is also you get a market differentiator. So you also need to think about that. I'll just use a minute to explain you how practically that would look like. So on the left-hand side, we have a traditional software development. So requirements, implementation, verification, release, and iteration. AI is, of course, different. The first thing we need to think about is to separate out the training and the serving pipeline. Yeah. So here you have requirements, you have data sources, model design, and model release, and you need to iterate on that. And then you have to have a separate branch to the serving. And here, basically, what you do is you take the trained models, you bundle them, and then you have two options: either to serve them in a batch way, so some sort of chunks, or you stream this. You make these models available to streamed inferences. Yeah, and then that's the two fundamental branches. which then need to also talk to the traditional software branch, of course, and there's going to be a feedback mechanism between them as well. And that's how the overall production lifecycle in the new world looks like. Um, how can you do that? So all of that translated into applications, you can do it ad hoc. You can build individual pipelines for different components, what I just explained, training using certain programming languages, your certain integration pipelines. However, that's very fast. That's impossible to monitor, scale, and maintain. So you need to say, well, I can do a quick prototype, but this will not be a scalable system. How to solve that? Look at the left side. You can create an expanding data science toolbox. So you let people or your developers use whatever, or data scientists or ML engineers, data engineers use whatever they like under certain framework. For as one example, use model as a data, meaning standardize your interfaces. So whatever language is being used or whatever system, the models are coming in a particular format, which can then be used into the serving pipeline. Similarly, on the serving side, uh, the software toolbox is typically static, semi-static, I would say, yeah. And here what you can do is, in order to control this environment that is coming through a very dynamic environment of the training pipelines and updates and so on, try to come up with a global unified framework so you can orchestrate all the resources and the models and everything. Um, I'm going to skip this slide in the interest of time, just so that I can show you two applications. The first one is from the automotive industry. Typically, when we have autonomous vehicles, they have all the sensors, and so that they can drive independent, automated in an automated way by sensing the environment around them. What they also need is certain mapping functionality, which is going to serve, or which should serve as a backup, in order that if a certain sensor fails, can we augment the sensor data through these mapping functionalities. Yeah, and in order to create that map, of course, you can do it by hand. Traditionally, have been done by hand, but this is really, really complicated. Some of the problems are it's slow, it's inaccurate, it's not really centimeter level accurate, so to say, across the whole globe. It's not scalable. We cannot do it again and again, and it's extremely expensive. The goal, come up with a certain automated way of creating these maps. So that's what we did. We looked at the aerial imagery of the world and created those maps by doing semantic segmentation on those pictures, and then stitch them together. Here I just give you some lessons learned from that. So starting from top left, we divided into 4 sprints, for example. Yeah. And each of them is a 3-week sprint. So the first sprint is look at the data sources, define the success metrics. Sprint 2, basically create lane marking models and individual deep learning models for different things. So this is also something to remember. You cannot usually, practically speaking, not build one model for everything. You have typically multiple models for multiple things. The sprint 3, make sure that you can cater different kind of inputs. Meaning, for example, if an image has a certain different resolution, will this model still work in that particular system? And also give semantics to your data. So if there is a lane detected, how can the system know that it's a lane? And finally, work on the entire pipeline automation. Lessons learned were data gathering. Of course, you can find some open source data on that, but that's at low resolution. High resolution data is really expensive. So data gathering is a critical piece here, especially in terms of investment as well. Then you have the pipeline topic. Pipeline automation is not as easy as you might think. And finally, the system integration, because such a map is not a product by itself. Rather, it's a service which has to be integrated into car vendor systems, for example. And you need to have that philosophy, what I explained on the previous slide in terms of global unified architecture. The second application, which I'll introduce in 2 minutes, is in the telecommunications area. And here, typically when you have a network, you need to plan resources. For example, if you're in area A and somebody is in area B, both of you want to watch something or communicate or whatever, the availability has to be really, really high. What that means is the network providers need to plan these networks so that the bandwidth and the resources are always available. Typically, this has been done using predefined rules or very cumbersome engineering models, or some manual fitting and so on. Again, all the problems what you saw on the previous slide, even though very different industry and a very different use case, the problems are the same: slow, unscalable, expensive, and so on. So rather what you can do is, again, you can automate part of that through an AI system, In this case, again, the 4 sprints, starting from top left. What are the data sources? That's a network topology, how the networks would look like, and what are the success metrics? Look at different features. If you look at all the network features, you have very, very high dimensions. So that's not a good idea. So reduce your features. Sprint 3, build a deep learning model with data augmentation. As opposed to, let's say, typical belief that telecommunications is a lot of data. Actually, it's very difficult to get that data to from the right stakeholders, because there are many, many, many different stakeholders who sit on this data, and it's not that easy to get access. So you will always need to have some kind of a data augmentation strategy. And finally, use different models. You don't always have to use the most complicated model. Use ensemble models and so on, and put it something which is integrable in your production system. That's the most important thing. Lessons learned. Keep it simple. Simple models are already improving the utilization rate by 10% in this example. Yeah. So earlier, let's say we were 70% utilizing the network. By those, we are doing 77% for example. Monitor the adoption rates. How much these models are used. Are these, let's say, machine learning models stale? If they are not getting used anymore because the designer is seeing that, okay, well, I can do better than that by manual, then nobody's going to use that. So monitor those things. And of course, educate. Have models which are explainable and show clear KPIs. To conclude, add end-to-end process thinking to your business unit so that use cases are more successful. AI is definitely sexy, and it's a huge hype. Everybody is doing AI. Production is not, but that's where the real value is. Yeah. POCs, your proof of concepts, will not scale if lacking a unified architecture. And finally, resource patterns. This is the slide I skipped for the sake of time. But you need to also monitor what are the resource patterns in terms of how much compute and store training takes, exploration takes, serving takes, and try to manage your orchestration pipeline based on that. Okay, so with that, I'm going to thank you, and I'm happy to take any questions.